whole team, bro.
Hold on.
No, I think next is from talking about papers.
Got it.
Oh, yeah, great. What do you want to do today? Yeah, yeah, I'll take it. If cool, I might have to pass today.
He asked you to
Yeah, we got next two, and I was like,
Different polynomial every time.
yeah, different. We can do some. Are you on campus tomorrow? Are you not there?
Know all that. And what about whatever you're going to say? But even then, it's not proper, the intuition.
We have to get an answer back by tomorrow to the graduate committee on the assigned.
I'm here for a lot of classes, so whatever I get, I should have compatible schedules.
Yeah, I think that Tom Miller would like to have an experienced GSI.
So today we're gonna talk about local and dynamic version of push level flow algorithm. And there are some applications like a local sparse cut and expanded pruning, which I will tell you what it is. So just to recap, push level algorithm, there are like there's some input, which is the graph, the source function and sink function, and then a parameter h. And what it does is that given any valid state, f and l, it will output the valid solution fl, f prime l prime. And just to recall what it means by valid state, right? Valid state means that if you given this label L, any nodes that have label at least 1, this node must be fully absorbed. And any edge that skip level, the flow must be fully saturated from top to, like from above to below. Okay. And then we will say that this state is a solution to if not just these two things that is satisfied, but no vertex. That is, every one that have label less than h has no access, so no active vertex. Yes. Okay. And we saw two algorithms. One is the algorithm, the basic algorithm that run in mh square. Another one is I record a video, so you can have a look. It runs in mh log n time. And the application of this, there are like two things that I mentioned. One is that we can use it to solve exact max flow, basically by setting h to be large, to be n plus 1 or more. So actually, what we really discuss is like a decision version of max flow, like checking if, given a source and sink function, you check if there is a feasible flow for that source and sink or not. But if you can solve this, then you can solve max flow just by binary search. Right? So you saw our decision version of max flow, and the key properties. By the way, I just want to recall that we use to say that whenever we find, whenever the algorithm return a cut, then the cut is really the certificate that certifies that there is no feasible flow. The key property is that when you return cut like this, let's say you return this cut, then you have that the flow out of the cut are saturated in the outward direction. So this is what we have. And the reason was, at least just to recall, how did we show this actually? Do you know? Do you recall?
Where the level is empty.
Yeah, we find a level K where this level there is no vertex. Yeah, so every edge going out of this cut a skipping level. So they must be saturated in the outward direction. Okay, so this is the key property. And actually, usually it's useful to find a cut and a pair of flow and cut such that you have the flow that's fully saturated outward from the cut. And but if you don't need to find to check exactly if the flow is feasible or not, or to solve exact map flow in other words, you just want to check. You just want to find some flow or find some sparse cut. Then just use H to be this much is enough. It either find you a feasible flow or return you a sparse cut. And the key property is that when H is this big, then when you find a cut, when there is an excess, you don't get a flow. When there is excess and you return a cut, the cut that you return is such that the flow is almost saturated outward. So this thing is almost as saturated as this, except that you have this much slack. So that is the sorry. So this is the key properties, and how to get from here to sparse cut. You can review the last lecture. Now I want to tell you about local algorithm. And by local, I mean that you want to solve some flow problem such that you don't need to read the whole graph. And how can we hope to solve something like that? Why is it possible in principle at all that to solve flow problem you don't need to read the whole graph? So we will try to develop an algorithm that actually, when you think about it, then it will mimic this some physical process. So imagine that you want to pour some water into the ice tray, right? You have this water, and then what will happen is that the water just keep it just kind of spread out, and so on. Okay. Some part is saturated, some part is not. But I think you can imagine how it looks like. So now note that this flow process is local in the following sense. Notice that the thing the water, just the time here is I don't know how to define time in this physical process, but the amount of things is just proportion to the volume of the source water. If you have small amount of water in the beginning, then it will spread maybe very small. It doesn't matter how large is the size of the ice tray, right? As long as the amount of work that this physical process is proportion to is just the amount of the water. So that is the intuition that we have in mind. So let's try to abstract this reason in the mathematical setting. So you think of each of these cells as a node in the graph. Each cell in this ice tray as a node in the graph. And note that the reason that this thing is local at all is because at least every node can absorb a large amount of water. Like if, imagine that if each of the cell here cannot really absorb anything, like let's say they cannot absorb anything at all except the last guy, right? Then if you pour water here, you will need to spread throughout the whole ice tray until water finds its way. So what you need is that, okay, each node should absorb some flow. And okay, so this is not true in general in generic flow problem. But at least it seems that we need this to make it local. The next thing is that every node here should forward flow to its adjacent node only when its sink is saturated. And this is really exactly how it is like in this physical process, right? You keep until you saturate, you never forward anything out. Now the nice thing about this property is that this is already how push level work, right? So like a node is never active until it has access. So you don't do anything on a node U until you are saturated. Okay, so this is the thing that you should we have in mind as a principle. So now, okay, so this is already satisfied by push level. So we can now, let's try to see what if we imagine that you solve, like we run a push level algorithm when every node is large enough sink. Maybe the running time is now local. So let's try to do this. So we consider this setting again. This is the parameter of the algorithm, a graph, source function, sink function, and edge. Now, by large enough sink for each node, I will say that each node its sink capacity is proportional to its degree. And by its degree, I mean like the unweighted degree here, like the number of edges incident to it. And let's say that everything is integral to like a source function is like it maps the node to an integral number, and the capacity is also integral. Now, if you run this, if given this input, then the algorithm will just do the same thing. Like given a valid state that can be initially 0 or not initially 0 too, as long as it is valid, it will return you a valid solution. So now, actually you will see soon that this thing seems like some restriction, but it's good enough for some application already, and I will tell you today. But the nice thing about this is that we will show that we can make some slightly make a slight modification of push level, and then solve this problem in this time. In time which is proportional to the total source in the beginning times h. So it doesn't depend on the graph, the size of the graph. So that's the setting. Is it clear? The setting. Okay. So now let me tell you how do we solve. Yeah.
So the source, you said delta V. So but you're saying that it should be at least So what if like all the sources are at least one? The initial, what do you say? The delta of V is at least one. So then it is like at least the number of vertices, right?
Yeah. So if the total source in the beginning is big, then the running time is not local. But if the total source is small, then it's
Right.
local.
Okay.
Right. Okay. So now let me describe the algorithm. So you see that like the algorithm will be like almost the same except some small modification. And I will tell you what is this modification. But before telling you this modification, what it is, I want to tell you why do we have it. Like we add this small modification so that because I want some additional invariant of the push level algorithm. And that invariant is this. I want to maintain that the access at any node is at most the degree. So unless this access is initially placed at U, so like in the beginning, the source might be very big, and so the access is big. But once, okay, so how the access evolve in this algorithm will be as follows. Initially, the access might be very big because the source at that node is big, but it will be such that the access can only decrease after from the beginning until it becomes 0, and then only after that the access can increase again, and then but when it increases again, it will never increase more than degree. That's how we want to make sure that this happens. Okay. And okay, so to maintain this thing, I need this red part below. So let me tell you now exactly what it is. So the algorithm is just here. Just like before, you just keep finding an active node. If there is an active node U, look at U. But okay. Let you. But now instead of getting any active node, we want a node that have small active and smallest label. Okay. So if this is the graph, and there are like a bunch of active guy, maybe here. So this is then you choose the smallest guy here, call it U. And once you choose an active node, then you just, okay, like before, check if there is admissible edge incident to it. If there is, you push. If no, you relabel. And what is nice about this? What is nice about this choice? Then actually, you know that if you choose this node U, and there is, let's say, there is an admissible arc here, V, then you know that the excess of V is going to be 0, right? Because V cannot be active. It just must have no excess at V. Okay. And this means that and the amount of flow that we will try to push is just at most the excess at U here and the residual capacity, and we have this thing. That is, we never try to push more than more than the degree of V. So this is basically now we get this invariant, right? So basically, you actually know that this thing is going to be 0. So you just said that we don't push more than the degree of V. So does the algorithm make sense? That's the only modification. So you see that like how the access on any node evolve is exactly as I described. In the beginning, the access can be big, and now it only like decrease because you will keep pushing its initial access out of it, and it will never receive any new access, right? Because when the guy that receives flow actually must have access 0, so you will never get any new access until that you like push out its initial access out of it. And when after that it might increase, but now it will never increase by more than its degree. Okay. So now we can analyze its running time. So it's clear that the algorithm is correct. It transforms valid state to valid solution, because what we do here is just we add some additional invariant and nothing else. Like we make the algorithm more restrictive actually. So we just need to analyze the running time. So the running time is gonna have like a similar flavor how to analyze it. So okay, we will claim that its running time is this, and so the total time that we spend on relabel, I claim that it's gonna be this, and the reason is that we only relabel node, like the node that has been relabeled will have level at least 1, right? But all of these guys that have level at least 1, they are fully absorbed. Like any guys that have level, this is 0 and this is at least 1, everything here is fully absorbed. But like let me tell you the intuition. Like if we have like small amount of flow from the beginning, it means what? It means that everything here needs to be fully absorbed, but you have only small amount of flow. So this set needs to be small, right? And we only kind of spend time on this set. That's why the running time is small. That's the high level idea. But now, okay, let me tell you more specifically why the running time is this exactly. So basically, if you look at the node U, whenever you call relabel, right, you charge like a degree of U. Like remember we charge the cost of degree U to each relabel. But what we can do is that each of these nodes here, you know that if this node here, it has already absorbed like a degree of U mass already.
Is that because the excess is greater than or equal to 0 for every node UN greater than 0? Like there's some excess because there will be some excess, and that's why it's in the greater level. That's why it is absorbed.
No. I mean because we really set the sink of each node to be degree.
Yeah.
So when we say that it is fully absorbed, then the amount of flow that is absorbed in this node is degree.
Yeah.
I want I will really just look. I don't care about excess here. I really look at the absorbed mass at U. Okay.
Right.
So each time that we relabel U, there is a cost of degree of U. If you remember the time to scan through all admissible edges that have the degree of U cost. What I will try to do is to charge this cost to the absorbed flow, to the absorbed mass. And but there are like degree of U absorbed mass at U too. So we can charge each of these unit of mass can be charged by just a constant, right? So the strategy is that at the end we will try to say that each of the mass that is absorbed is charged at most h. So that's why the total cost is going to be like this. So the point here is that every time you relabel U, you have this amount of absorbed mass, but you spend this much time. So each of this guy is charged a constant. And how many times that each unit of absorbed mass can be charged? Just h time by the relabel. So that's why the total absorbed mass, since the total absorbed mass is at most this much, the initial mass in the beginning, so the total time is this. Make sense? Okay. So if I need to describe it in a more algebraic way, then we can say that the total cost that we spend on relabel is just on this guy with level at least 1. Each of this guy is relabel h time, and each time we relabel, we charge this amount of cost. We pay degree amount of cost, but this degree is just at most the absorb of U. So this whole thing is at most this. But the total amount of absorbed flow, amount of absorbed mass is at most the total amount of initial mass anyway. That's why the total cost is just this much. Just another way to say things. Okay, so that's the total cost that we spend on relabel. How about the total cost that we spend on push? To do this, I will just bound the total number of push. And each push costs you constant, so that's give you total cost of this. Okay. So now we will look at this potential function. Okay. And so note that each of the push will decrease this potential function by at least 1. Right? Because first, every time, this is where I need that sorry, one second. So because why is this? When you push from U at level I to some node V at level I minus 1. Right? So you really just move excess from I to I minus 1. So if you push by psi, this thing will just decrease by psi. Okay. And why is it the case that psi is at least 1?
Because integer.
Yeah, this is because now we talk about everything is integral. Yeah, good. So this is the case, this is the reason why I need the integral flow. But yeah, now, okay, every push decrease potential by at least 1. Now we just need to bound how much this potential can increase. And it can increase only by relabel. But when you relabel U, then you increase this thing by the excess of U, right? And now, suppose actually, okay, there are like a two case now. If the excess of U is more than its degree, then it means that all the excess that U here is actually from the initial excess, from the initial source. Right. So what we will do is that we charge charge 1 to each of these initial source, initial access. And each of these initial mass here can be charged at most h time. Right. So for each mass that you put into the system, it can be charged as an initial access at most h time. Okay, that's one case. Now, suppose that an excess of U is less than this degree, then you know that like excess is less than absorbed, because absorbed is degree. So instead of charging to the excess, you now charge to the the absorbed mass. Like the amount of thing that increase is excess, but you charge to the absorbed mass because this thing is less than this. Charge 1 to each of the absorbed mass. So now each unit will be charged as an absorbed mass at most h time too. Why is that? Because when a unit of mass is absorbed at a node U, it never leaves U, right? So, and U can increase at most h, can increase its level at most h time. So just to conclude, we basically we charge the increase of this potential function to the initial mass, and each mass can be charged basically h time as an initial access and another h time when it is absorbed at some place. So in total, this thing can increase potential by at most the total mass times 2h. So the number of push is this much. Yeah, so that's it. That's why the running time is just kind of proportion to the initial flow. So quick question: suppose that everything here is not integral, but it is like a half integral. Then what would you have?
The constants would increase.
Yeah. Like the cost can increase by at more than constant. If this is d, then the total cost is increased by d. And the reason is that here instead of 1 you have 1 over d. Okay. And then the total cost is this times d. Okay, so now let's see the quick application of this algorithm. So imagine this setting. Like you have super big graph, just so huge. You don't want to read the whole thing. But you want to find, like you kind of know some initial like knowledge, like prior knowledge. Call this set A. Someone is giving you A and promise you that there is some sparse cut near A. And by near, I mean this. I mean that there is some phi sparse cut such that it kind of overlap a lot with A. So think of this sigma as maybe 0.9 or something. So most of the volume of S is kind of close to A. Okay. And what we want to find is like, okay, you know that there are some sparse cut close to A. Now you want to find a sparse cut, but you don't want to read the whole graph. So A itself might not be sparse at all, but how to find such a sparse cut? You might not return S exactly, but you might return some other like S prime that is sparse, but that's fine. Okay. So what we would do is just call this local push relabel algorithm, and with the following input, we will set the graph GC is just a graph G such that every edge capacity is 1/5. This is just like before. And now the total source is, it makes sense to put the source to be like every node in A, because like the idea is that you try to push flow from A, and if there is some sparse cut near A, you should get stuck. Yeah, that's the idea. So by how much I put the source on each node in A, it's gonna be 1/sigma. Okay. And every node in B, every node is a sink of this capacity, just like we require for a local algorithm. And I set H to be this much. Okay.
What was phi here?
Phi is a promise, like phi is a promise that there is some phi sparse cut. Okay. All right, so now can this algorithm terminate with no excess? The answer is no. Really, by how we design the flow, like the source and sink function. Because basically, the idea is like we just try to define the source function such that it is large enough so that it got stuck, like it must got stuck. Like it cannot go out of S basically. Yeah. But it shouldn't be, the source should be large enough so that it got stuck in S, but it should be small enough so that the total running time is small. So we really just set it to be such that we know that it will got stuck for sure, but as much as that is enough. So just let's verify that the source must get stuck at S star, the promise. Like the total source, the total initial source at S is what? It's just for every node that is in the intersection of A and the sparse cut. And so the total source is this thing times this. But this is at least here, just from the promise. But yeah, what is the total amount of, like, the total capacity out of S star in GC. This is 1/5 times the size of the cut size in G. But this is sparse, 5 sparse. So this is less than. Yeah. So we know that you will get an excess for sure.
Because it is big graph, we take volume of S star as minimum. So the minimum volume. So
Say again.
that equality only holds when volume of G of S star is minimum, right? S star.
Oh yeah. So let's say that G is so huge and S star is like a small. But we need this that S star is the smaller side of a sparse cut. Thanks. So now, because we know that no matter what, we know that it will terminate with an excess for sure. So there is some node with a reliable edge. So once we know this, then we will just try to do the same thing like last class. There are node on level edge up to level from edge up to 0. So we will find some cut using the same argument like in the last class. It will be such that this cut it will be sparse. So you should try to follow the analysis from the previous class and verify that you can find this level cut K that is sparse. Okay. So the cut will be sparse. This is just clear from it's just from previous analysis, but actually you will know that the cut that you return must be small too. Actually, it must be small also just because the total running time of your algorithm is small, is local, so your cut must be local. So the total running time is this. But actually, you know that the cut size will be smaller than even this much. There's no factor of h. And the reason is here. The reason is that everything that you return here, these guys are fully absorbed. So the total volume of this guy is just the volume of this guy is really the same thing as the absorbed flow of this guy. But the amount of absorbed flow is at most the total flow in the beginning. And how much is the total flow in the beginning? Is the volume of A over sigma. So we know that the cut that you return is small, and the running time is this, which is something like this, something small. By the way, you see that there is some still small dependency on the size of the graph, log n here. But you should try to see that if h instead of log n over 5, you set h to be this much, it will work too. So yeah, exercise. Okay. So let's conclude. The conclusion is that if you have a vertex set A, like a promise, like some prior knowledge, such that the volume of A is not too big. Actually, why do we need this, you know? Like we put the total mass, we put the mass here, each of these, you get One sec. Sorry. This should be this thing times the degree. Hey, yeah. So that's why you got stuck, right? Yeah. Yeah, everyone agree, right? This should be this times the degree. Yeah. Okay. So actually, what would happen if the volume of A is strictly more than this thing? Does anyone see a problem? So what will be the total initial mass in the beginning? The total initial mass in the beginning is the volume of A.
The whole volume, like our graph.
Yeah. Yeah, like the total mass in the beginning is this thing, but the total sink in the beginning is this thing. If the total mass from the beginning is just even more than the total sink, then you know that like the flow might got stuck, but it might got stuck when like everything is absorbed, and so actually you don't get like any cut. Yeah. Like so.
This is similar to where a local cut we have mu less than m over k.
Yeah. Yeah. Exactly. So, in order to like for the push level to work, you need that there is some guy which is not fully absorbed. Okay, so you need this, but this is like a small my assumption, just because we are thinking about like huge graph anyway. And we said that okay, if there is some sparse cut S star, such that it kind of overlap quite a lot with A, then you can find a cut that is sparse too, and this cut is not too big. The volume here is this much in this time. Okay, question about this? Okay, so basically, I just want to tell you some big picture. Like this algorithm is just one of the algorithms that we call local clustering algorithm. So now we have seen two local algorithms for finding cluster in some sense of cluster. One is the just today local push level to find local sparse cut. Another one is local Ford-Fulkerson, the sometime before, the one that find local cut of size at most k. There are like some different kind of algorithm based on random walk and page rank. Very interesting too, but we don't have time to cover. But there are many other interesting questions about local clustering. What if you want to find local set that is dense, or like a local set that have a lot of triangle, or so on? We can like people ask about this thing. Like data mining people really like this kind of question. Yeah. So, and it's interesting in theory too. Like so if you want to think about this, we can think about it together. Okay. So that's local sparse cut, and now I will talk about expanded pruning. So it's gonna be some like recall the very first lecture when I talk about the robustness characterization of expander. Can anyone recall what we say about that? Like
against deletions.
Yeah.
When we delete
D edges.
D edges we only restrict D over 5 volume.
Yeah, like only D over 5 volume can be disconnected. Yeah. Right. Now we're gonna say something stronger. It's gonna be much stronger characterization. So, and the question in high level is about how to repair an expander. So what do I mean by this formally? I mean the following. Suppose that you are given a phi expander from the beginning. This is phi expander. And let's say that I want to delete some set of edges called D. I might delete in such a way that something is cut out. I might delete something else too, but maybe it looks like this. But this is still connected. But it might look like a sparse cut here now after deletion. So what I want to find is that I want to find something called prune set. So let me denote G prime by the graph after deletion. I want to find prune set such that let's say the prune set look like this. So such that after I remove the prune set from the graph after the deletion, this graph is an expander. Not as good as phi, but still like a constant time phi. And the prune set here should be small too. By small, I mean D over phi. So we will show actually how to solve this thing. So this can be done. And you see that this is really like a kind of a strictly stronger notion of robustness. Because in the first lecture, after the deletion, P here is small, like before. But we only have that the remaining part is connected. Right? Basically, it's easy to define P. It's just all the small connected component. But this characterization says that no, it's not just saying you don't just want this to be connected. After you carve P out, after you prune P out, the remaining part is still an expander. So expander is super robust in this sense. Like you just delete something, it is still expander actually. Okay, and not just here actually. We will show something even stronger. You will show that we can repair an expander under a sequence of deletion at all time step. So the setting is here. So this is like a real expander pruning. Before I just call it one batch expander pruning because all the deletion is come to in one batch. Now the real expander pruning is here. You start with an expander, and there is an online sequence of edge deletion. And let's say Gi is a graph after time I. And what we want to maintain is that we will maintain a prune set called Pi to be a prune set after time I, such that after time I, if you delete the prune set, then the remaining part is an expander. And the prune set cannot grow too fast. Like in the beginning, it's just empty. In the beginning, I is 0. And at each time, it can grow only by small amount. And it only grows actually. Yeah. So let me, show you. Some animation. Yeah, so, okay. So you start with an expander, right? And then maybe deletion comes. and you kind of find a P1, and the complement of P1 is an expander, and so on. Like maybe the next edge is maybe even not a deletion, can be insertion too, but let's focus on deletion. And then P1 can grow a bit, and then and the complement of P2 is still an expander, and these things like a complement of P remain an expander at all time. Yeah. And the update time will be actually small, and the set P grow very slowly. Yeah. So like in some sense, like each update really like cause like just small problem to expander. The remaining part is still good. Okay.
By proving, you delete the both edges and the vertices.
Yeah. I really just look at the induced subgraph of the complement of P. Like, I really delete this node and edges incident to it, and the remaining part here, I mean an expander. Okay. And obviously, expander is necessary because if there is a sparse cut, if you delete like a 2 edge, then what you need to prune is this much already. So, just want to mention quickly that if you know how to prune an expander, then you can make your expanded decomposition dynamic. Why is that? Like, you can just start with finding an expanded decomposition, and when there are like some edge deletion into the graph, if the deletion is here, you just prune here, and so on. So the remaining blue part is remain an expander, and the total amount of thing that you prune is going to be small as long as the number of updates is small. Right? Because we promise that the prune part grows slowly. So as long as the number of updates is not close to linear yet, even if you treat this whole thing as an intercluster edges now, this is the valid expanded decomposition still, right? Because all you need about expanded decomposition is just that all the components are expander and not too many edges crossing.
You mean
in
each, like if you go to that decomposition, you mean every vertex in these P's are like an expander on its.
Yeah, a singleton expander, like a trivial one. Yeah, so basically, like, if you want to maintain expander dynamically, once you have expander pruning, you're done. You can get dynamic expanded decomposition. And like, this actually was the key to many dynamic algorithms. Like, we use it to break. Like, there was like a long-standing open problem that people cannot improve the update time of dynamic connectivity. It used to be root n. We make it like small, and we can use it to solve everything. So like it's very like an important tool for dynamic algorithm. Okay. The point I want to make is that it is important too. So the reason is just like expander are just so great, but everything we talked so far is just for static algorithm. But expander pruning allow us to exploit expander in the dynamic setting because you keep repairing expander. Okay. So I will tell you how to solve a one dash version first, and maybe I will need another time to record a video about the dynamic one. Okay, we will need some terminology. First, let's assume that the graph is unweighted, and like everything actually can be generalized, but let's assume that the graph is unweighted and the graph G, and let's say this is a set U. Then we will look at this thing. So not like induced subgraph, but with this this thing, brace parenthesis. So we call it induced subgraph with the boundary vertices. So what do I mean by this? I really mean that just start from the induced subgraph, but for each of the node, for each of the boundary edge here, I just like create like if this is an HE, just create a vertex here, vertex XE here, and so add this edge into the graph. Right? So the graph look like this basically. This is your graph. It's just induced subgraph, but with some boundary vertices. So I call this. Let's denote all of the boundary vertices by this thing. Okay. And we don't need this. Okay. And I will say that this thing is a near expander if you look at, so let's say this is U. Is a near phi expander if you look at any set S such that the volume is less than half, then the cut size is at least phi times volume. So this is like almost like before, like expander, except that when you look at the cut, you look at the cut inside U, and you don't count just the edges crossing this, but you count the edge here too. So like you use boundary edge here to help you expanding. Yeah. Okay.
So if the volume of S is again calculated in the G of curly braces U graph?
The volume of S is calculated in here. Everything is calculated in G brace U. So note that, by the way, note that when you talk about this, the nice thing about this induced subgraph with boundary vertices is that the degree is preserved, right? Every node here have the same degree as before. So the volume of every set in this graph is just the volume in the original graph. So it makes sense to talk about degree and volume as if we don't refer to the induced subgraph. Okay. So now let me reformulate the problem a bit. If you can solve the following problem, then you can solve one batch expander pruning. So what is that? So I will say that, let's say that we are given a near expander GU. This is a near expander. Yeah, near expander. not expander yet, it's a near expander. And what we want to find is to find some prune set P such that, and let's say U prime is like U minus P. And now we want to say that the induced subgraph without boundary of U prime, this thing now is an expander. And P is small. By small, I mean proportion to the number of boundary over phi. Okay, so that is we want to make a near expander an expander by pruning. So let's see why we like the problem reduced to this thing, right? Like suppose that so imagine the expander pruning setting where you have an expander and you delete some edge. Look at this graph. You delete some edge here. Now what we will do is just let's create another graph G hat where for each of the delete edges you create this. You delete this edge, but you create the boundary edges. Yeah. So observe that this thing now, like this thing, is a near expander. So why is that? This is just because if you look at any set, right? So maybe if you look at any set, maybe this set. Yeah. Maybe look at this set. The cut size here in this G hat V is at least the cut size in G. So why is that? Like for every edge here that used to be here, you count it. But if this is the deleted edge, you also count it here. Yeah. So the cut size is like not reduced for any cut. But G is an expander, so this is at least the volume of G. But the volume is preserved after you look at this like the volume of this thing is like the degree of every node in G hat V is preserved in G. So now you have that G hat V is really a near phi expander. Okay. All right. And now, so you can see that if you can find a set prune set which is small in G hat V. By small I mean this small this much, right? But how large is this boundary? It's just D in original graph. Like this is basically D over phi in the original graph of G here. So that's why you will get that the volume of P is D over phi. Yeah. And you also have that if you prune this thing and you say that this thing, the induced subgraph here is if the induced subgraph here is a phi expander, if this thing is a phi expander or phi like a omega phi expander, then note that this is really just a graph. Like if you look at the induced subgraph here, it's just a graph that you delete it's just the same graph as induced subgraph in G after the deletion, right? Because all of the deleted edge you make it boundary edges, but but here you look at the induced subgraph without boundary edges. So if this thing is a phi expander, then this thing is a phi expander too, which is what we want. So now you agree, right, that now the problem reduced to pruning a near expander to be an expander. Now we can just focus on this problem. Okay. Okay. Now there are like some useful structure to look at. So let's say that this graph GU is a near expander, but suppose that like we are not done. We're just not done trivially. Suppose that G induced U is not a 5/6 expander. Then there is some nice structure going on. I claim that there must exist a cut S. There must exist a cut S such that the edges from S to U, from S to going out of U here, I call it C here. This thing is much smaller than the number of edges from S to outside of U. And then this I call it B. Yeah. So C here is for cut, and B here is for boundary. So C is less than B over 5. Okay. So why is that the case? Okay, but is the claim clear? Like, okay. Why is that the case? This is because, okay, if S is a sparse cut, if S is a phi sparse cut inside G induced U, if S is phi sparse in GU, then by definition C is less than if S is 5/6 sparse in GU, then C is less than 1/6 phi times V, where V is just a volume. But you know that G brace U is a near phi expander, so C plus B actually is big. So C plus B is big, but C is small, so B must be much bigger than C. That's the idea. Okay. So C is small, C plus B is big, so here B must be big. And if you do the math, C is less than B over 5.
Here we have different volumes for S in G brace U and G bracket U.
Yes, so actually C is less than this phi times maybe C V prime, where V prime is the volume in G bracket U, but V prime is less than V.
Yeah.
So volume of S in this is less than volume of S in this. Yeah. Okay. No, because here you don't count these boundary edges, right? You see, right?
But we have edges inside them, right? We don't have boundary edges, but we have edges between A and B.
Yeah.
But G currently doesn't have edge between A and B, but it has boundary edges, right?
No. No. Here, now I really like talk about the graph. Like we have reduced the problem to pruning near expander. Now we don't talk about original graph at all. So there was like there is no edge here. Yeah. Okay. By the way, if you say that GU is like not phi, like it's not phi over 1000 expander, then you would have that C is much smaller than B. Yeah. Just use the same argument. So you should, when you think about this, you should think like, okay, if G bracket U is not an expander, then C is much smaller than B. That's how you should think about it. Okay. And now, I'm out of time. Sorry. Let me just do this. I will just continue the lecture on Friday. We will not like talk about exercise. We will just continue doing the lecture. By the way, tomorrow from 8:30 to 10, I emailed undergrad student that maybe we can I want to give some chance so that people can ask me about any material from the class. So I would like to focus on undergrad, but if any of you would like to come, yeah, you're welcome. Yeah. But we will not talk about anything new, just about asking any question. Yeah. All right. So either see you this time or this time tomorrow. Then.
Where is that?
Zoom. I will send the link today. Yeah.
Exercise is also on Zoom.
No, exercise is at the same room. Okay, then see you tomorrow.
Oh yeah, might be good.
Yeah.
Okay, sure.
Name tags are right here. Come and grab. I'm using them. That's a while ago. Sorry for the disorganized there.